Yes, so this is our airframe. This is the upper forward airframe. This assembly that we've got. Got a nose cone and connected to the tube by shear pins, and then we've got our parachutes in that bay, avionics, and everything else is below that. This is our selection for nose cone. We're planning to buy the 8-inch 5-to-110 in O guide from Lawman. Cool aluminum tips, as you can see in the photo. And we plan to make a little aluminum cylinder to epoxy inside that we can mount our bulk plate to. And it's going to contain all our payloads.
Might try to epoxy an aluminum cylinder. Can you just use a set screw or something?
Or we can do that. Yes, that's true. We could use a set screw. Well, with a set screw, though, we have to worry about the tube still fitting in, or just wouldn't stick out at all.
No, there's a decent amount of material there.
Okay.
You just put it on there, you just get it flush with it.
Okay. Yeah.
Because unless you're using a specialized epoxy, it's not going to stick to the metal.
I see.
So unless you're going to buy a specialized.
All right. And it's removable too, right?
Yeah, it is removable too.
All right. Perfect. Here's some more details on our payload bulk plate, which is going to be what one payload is mounted to. I decided to choose aluminum 6061 for it. It's over a 1.5 pounds heavy, and we chose 0.3 inches. I think that number for shearing is very low, so we didn't actually. I don't remember looking at the yielding numbers, but I think this is thick enough. For the eye bolt, we chose a 9/16 eye bolt made out of steel, rated for 3,000 pounds. We're expecting about 1,500 to 2,000 pounds at main deployment. So we decided that this was enough, and we're going to mount it with a washer and a nut. This is our forward airframe tube. We chose a 4-foot piece of G12 fiberglass, 8 inches in outer diameter, about 7.8 in inner. And as mentioned earlier, it's going to be pinned to the nose cone with shear pins, which break off during deployment. And at the bottom, it's connected to the aux tank via a coupler, which will be covered when Prop presents it. And we plan to make a hatch in it to access avionics more easily.
What size are those shear pins?
I think they're 440.
Is it going to be enough?
To hold like the weight of the rocket. Yeah, it should be. I can double check the numbers on the website, but
You guys are about 100 and
almost 120 dry.
yeah.
Double check that. Here is our proposed deployment scheme. So we're going to pop off the nose cone. The thing will shear off once we set off black powder charges, and it'll descend first under drogue, as shown on the left diagram, and then up at about 500 feet above ground level, main will deploy. The turn descenders will break, and main will be allowed to unfurl, and will return to the ground safely. Here's some of the deployment hardware that we're choosing to use. We calculated we need about 6 grams to produce 8 PSI inside the parachute bay, but we'll do ground testing and maybe go up if we need. And for that, we have aluminum charge wells, which I believe are able to hold up to 8 grams. We can also machine our own if we need to, and also it's a good practice to get our team some machining experience. We plan to stick 2 E-matches inside each charge well just for redundancy purposes. For main deployment, we have this turn descender sort of loop configuration, so that if either turn descender breaks, the whole loop will break off and main will be allowed to inflate. And we also plan to add in extra E-matches in case there's errors with them.
We're going to post what channels you're going to put the extra E-match in.
I'll call that.
In the tendons.
Yeah, so you have 2, 4, 8 E-matches on this thing. How many channels do you have for your altimeters?
Oh, so we're putting them on like the same channels, and then they'll be connected to regular connectors. So it's like we'll have multiple E-matches in the regular themselves, not in the actual 2 terminals.
So you're trying to get both of these to go off at the same time?
Yeah.
Okay, well, we'll wait till the avionics section.
So they could both go off. And this is our parachute selection. For drogue, we have a 42-inch elliptical from 30 shoots. we simulated that under drogue, we would get a rate of about 80 feet per second. And then when main is the extra large sky angle chute. And that will deploy, as mentioned, at 500 feet above ground level. And that gives us 20 feet per second when we get back to the ground. And for shock cords, we've decided to use 1/2-inch tubular Kevlar from One Bad Hawk.
And that's with the avionics bay boat plate. It's gonna be aluminum 661, so 3.26 pounds, and it's gonna be thickness of 0.75, and required thickness of Brent shearing is 0.06. About the same calculation for the boat plate. And it has the same eyeball hole for 9/16 inch, and then 6 radial holes for. And then down to the aft airframe, there's gonna be the 3 main components with the hatch with the cover to be able to have access to all the prop valves. Then there's a motor centering ring, which is gonna be made out of aluminum with 3 1/4-inch radial holes to make sure the motor stays centered while the motor is being used. And then there's also a bow tail, which its main function is to transfer the load transfer the thrust to the airframe, and then also help aerodynamically to reduce drag on the rocket. And then a little more about the bow tail. It's made of aluminum, and its mass is 5.7 pounds. And it's gonna bolt onto the combustion chamber with 6 radial holes, 1/4-inch holes. And then the airframe is gonna sit on the lip of the boat tail and be bolted together. It's gonna be 6.5 inches tall, and it's gonna converge down to a 6.3-inch diameter. And then, so the fins, they're gonna be made out of G10 fiberglass, and they're gonna be cut from send cut send. And then the shape, it's a trapezoidal fin shape. And there are the main dimensions on the slide there. And then, so since we're gonna do a epoxy fin layup for the fins, so then this is a model of the jig that's gonna be used to help lay up the fins. It's gonna be 3D printed with PLA, and it's gonna friction fit to the airframe via that lip there on the jig. There's gonna be 3 of them printed to make the full circle to make sure each fin is 120 degrees apart. And then the fins are mounted 1 inch above the bottom of the airframe. And then, so yeah, so 3 of the fiberglass fins are gonna be attached to the lower airframe via the epoxy fillets and layups using that jig before. And for the layup, there's gonna be 3 layers with 6-ounce fiberglass weave. And it's gonna be alternating the direction between 45 and 90 degrees to increase the strength. And then there's gonna be 2 layers of peel ply and then Mylar on top of the laid up fins with the fiberglass. And then so we're gonna use a sandbag to help squeeze out the excess epoxy. And we're gonna be doing like 1 side at a time. So we're gonna do this 3 times. And it's approximately gonna be like 0.25 inches thick after all the layups done with all the epoxy.
These have drawings, what do you think?
For
Any of the parts you're machining?
we haven't produced those yet.
But how would produce them? Typically we want to see that during the CDR, right? Actually look at the drawings, make sure the dimensions are right and whatnot. Because if you go back 1 slide, because like having the drawings up, we could be able to determine you're putting your rail buttons on the fasteners for the tail cone, right?
Yeah.
Well, do you know if that rail is going to fit? So if you put 2 rail buttons on those things, right, is it going to interfere with that fin?
Right.
Right, we don't have a drawing to catch that, you know. So, will you guys, I know you guys are doing exams and whatnot, and it's gonna be pretty much dead the rest of the semester, but before you start machining, definitely before you start cutting anything, let's have all the drawings laid out and just, you know, go over it and because like if that off a little bit right now, your rail buttons are in line with your fins, or it's just rubbing up against the fin, right? Something silly like that. So
Yeah, it's not good.
Sure. Well,
Hey, can you guys hear me?
Yeah, we can hear you.
Did you go over what your attachment to the airframe for the shock cord is? The God bolt?
Oh, yes. That's on our avionics bolt plate. That's that 9/16 eye bolt that we had on there.
That's that 9/16 eye bolt.
Right there, yeah.
Okay. Chris, does that 2,000-pound strike force seem reasonable?
I lost the last part there. I mean, it looks fine to me.
It looks okay. It just bolts into the airframe.
Oh, you mean radial weight? Yes, we have 6 radial bolts that go into the airframe.
Okay. They're quarter bolts. All right. That's what killed us last time. Just, yeah.
That was your horizontal velocity, right? I think it should be.
Can y'all hear me?
Yeah.
Okay. Yeah, along with what Kayla was saying, I would make sure to have, I don't know if you guys were planning on doing any FAA with the fiberglass, but that has been like what majority of teams have failed is with the shear for that. So just be careful, do some calculations.
FEA with composites, and we're not, I don't know, it's pretty hard. We'll try to get some things, but it's kind of impossible right now. The skills we have.
We can test it. We test it physically.
Apps too, but that's kind of what goes to too.
Any other questions? So I'm Colin, I'm the avionics supervisor. Yeah. Windows there. F11.
If you right click on it, you can unpin it usually.
Taskbar.
Yeah.
Up and just go.
So I'm the avionics and payload lead. This side is our avionics bay.
Okay, so our avionics bay has two plates of G10 4-inch thick. Forward and the back. And the back plate has the 3 18650s mounts and a mount for our camera. And then it folds into the bulk plate using 2 4-inch threaded rods, both 8 inches long. Outer diameter or diameter of the entire avionics bay is 7.9 inches and 7 inches in height. And we're gonna use 16 Wago connectors, 8 for each charge wall and 4 on top and 4 on the bottom to basically wire from the telemetrum and our SRAD avionics board into the charge walls. And we have 2 screw switches on over here. Is that?
Yeah, so we have the 2 screw switches, and in the middle image here, you can see where it lines up with the airframe hatch. So that's how we're gonna arm the avionics bay. And in order to have ease of access, we made the boards able to slide out. So you can kind of see down here, there's like channels where the avionics boards can come out together, and that way we can work on them. And then the Wago connectors are on both sides, so then we can disconnect our power channels and pull them out. Any questions on that? So for our avionics, we have 2 avionics boards, COTS avionics boards, the telemetrum and the egg timer proton. And we're currently developing an SRAD avionics board. And these are some of the specs. with the telemetrum, there's live telemetry and flash storage, and with the egg timer proton, there's only flash storage. And our estimated battery life is 27.5 hours for the telemetrum, and estimated for the proton and SRAD will be 24 hours. Any questions? And these are the avionics board layouts.
Yeah, so this is the board layout for the avionics bay. You can see the front plate and the back plate, and they're both to scale here. You can also see that we have all the batteries on the back plate, and you can see the kind of battery holder that we're using in the bottom right image. And you can see all the wires as well as the connections that go in between the plates through the screw switches and into our different components.
Where's the egg timer at?
Sorry.
Where's the egg timer at?
Egg timer. So the egg timer is if our SRAD doesn't work, so that's why we currently have the SRAD on here. But if the SRAD has not been fully tested by the time we want to launch, the egg timer will take the place of that.
Any other questions?
Do you plan on flying your SRAD board and any other rocket beforehand?
Yes, we do plan on testing it in an L1 before. L1 size rocket.
Does the SRAD have its own antenna or is it using the
So it's connected to a transceiver, which is connected to an antenna. Yeah. Any other questions? So this is the overall architectural diagram. So you can see at the bottom, we have the SRAD and the egg timer interchangeable. And then the telemetrum, and then they're connected through 16 total WAGO connectors, 8 on each side. And then they're each connected to, so each WAGO connector will have one connected to the first fire charge, and then the second fire charge will be connected to the second charge well. So then we'll get redundancy there, and then you can see our ground station system there. And then this is an overview of our SRAD avionics board that we're building. So we're designing it in Altium Designer, and all the circuits will be simulated in LT Spice. We're using an ESP32 microcontroller for wireless arming and control on the launch pad. And we'll have about 8 hours of onboard SPI flash storage when we're recording data from all our sensors. We'll include a high G accelerometer for if there's a fatal deployment error or some sort of error. And our barometer is sized to go up to 100,000 feet, so that should give us a good margin. And we'll be using GPS and IMU for positioning and state detection. And we'll have 2 power channels of protection circuitry as well as continuity detection. And it'll be powered by 2 18650 lithium-ion batteries in series. So here's the software diagram. Vidya's going to go over some of our logic for deployment.
This is our diagram. And as you can see, about 100 times a second, we're going to collect data to transmit and store it. And we're also going to use that 100 times a second, we're going to check our compute velocity and decide what to do. So before we can do anything, it has to be armed. And the requirements for that is that the screw pitch has to be installed. It needs to be vertical, and from a computer it needs to be armed. So it cannot go off by itself. For takeoff, once it detects acceleration of 3G, that's if prevents it from anything if the rocket's dropped. It can't consider a takeoff and it can't launch the charges.
It detects when the boost is over, by when the acceleration starts falling again, so when acceleration downwards is greater than 0. Then it needs to find out when it's subsonic. So it uses its velocity, which is based on the IMU and a Kalman filter. And that, so when things were subsonic, that to be less than 300 meters per second. Then it starts using the barometer to wait for the aperture detection, which has to be subsonic, and the pressure change of the average pressure of the last 2 1-second periods difference has to be positive, should be when it's falling. And then second parachute uses the barometer to detect when it's 500 feet above ground level.
How are you gonna test your supersonic logic with an H motor?
Supersonic logic?
Yeah, so you consider you're gonna fly it on a small rocket, but like you're gonna, part of this is your Mach walk out. How do you plan on achieving that with a rocket that goes 150 miles an hour?
We'll likely have to like make a fake criteria, so it's like below a certain speed that will actually hit on the smaller motor. And then just make sure our acceleration integration to find that velocity is correct, or something like that.
Like we can compare, like for subsonic, we can also still look at what's it called, barometer detects, and we can see if it lines up with what we think the velocity is based on the accelerometer. And if that works, we can hope it works at some supersonic speeds too.
Okay.
Yeah.
Test like you fly. Surely somebody here has a rocket you can stick that on,
Yeah,
right? How big is this thing?
2 by 3 inches.
Let's get a tube and a motor. I mean, seriously, like. We have plenty of motors in storage. Right, we have plenty of tubing, just slap them together.
That's cool. Any other questions from people on this?
See the avionics. Is the end of the avionics section?
There's the ground station, but yeah, that's.
Oh, one more thing. Add it. So for, we're also gonna have like a timer lockout after it takes off to detect when we're subsonic. So in case if something goes wrong with the accelerometer, it can't launch the parachute while it's still, the rocket's still running.
So our ground station will consist of 2 laptops, one with the teledongle connected to the telemetrum running Altus OS, and the other with the Arduino Nano connected to our SRAD board. And that'll be a LoRa transceiver module, and we'll be running Arduino ID with the terminal open to see our position, as well as some basic data sent back from our SRAD. And we'll have 2 Yagi antennas tracking the rocket using our antenna tracking system that you'll see in the payload section, and then also 2 Yagi antennas tracking the rocket by hand, if there's any error with that.
So one comment I have for the avionics, it's gonna sound really silly, like a joke, but it's not. It's been at least 4 years since a team's avionics has worked the first time at a launch. Okay, and it's always the delay. So what I would recommend, and what I'm recommending to all the teams, is really pushing on it, is that even though it sounds really silly, before the launch, like before you even schedule the launch, figure everything in the configuration is going to be in, and actually just do it outside.
Okay.
And like do the whole thing, because it's been 4 years. Like actually back in like, went through the my records and whatnot after the HA launch.
Yeah.
It's been a long time. So let's break it, right? Let's
Yeah.
not do that.
Any questions from the Zoom on avionics? Okay. So moving on to the payload section. Our first payload is the water ballast. This will be up in the nose cone. And they'll have 500 milliliters of water dispensed through a tiny hole in the nose cone. So we have the syringe in the middle and a tube will be connected to that and out the side of the nose cone. And the expected mass is 2.5 pounds. And this will be controlled by a secondary SRAD board, the same SRAD board as the avionics board, but we'll have a second one that we'll build. And it'll be controlled by that to deploy at altitude. So yeah. And then we have the 418 payload. So this is a payload from Aero class, and this will be going in the payload bulk plate, which is near the top of the rocket, also right under the water ballast. And it's a fully contained system, and it's about 1 to 1.5 pounds. So yeah. And our final thing is ground station antenna tracking, and Megan will talk about that.
Yeah, so this is more of our experimental tracking system. Will still be doing tracking by hand because this is not 100% sure it will work. But basically, it's controlled by 2 servo motors, one that's in charge of the azimuth and the other one in charge of elevation. The azimuth is going to be used in that bottom depiction. It's going to be 3D printed gears. And then the top one is going, since that has most of the load, it's going to have, we're going to buy bevel gears and use that. And so we're going to have 2 Yagi antennas. This only has 1, but it's just going to be that, just another pole to it. And we're going to, so, and the current plan is to have some flight computers that will help the Arduinos track the signals from the rocket. And that is how we are going to track the rocket to get the best possible connection. And yeah.
And that's the end of our payload sections. I don't know if you want to go back to prop or
Yeah. Do you have anything you wanted to comment on for airframe or avionics?
No, other than just, let's look at the drawings before you guys cut anything. Real.
Yeah.
And then I'll test like you fly for the
Yeah.
avionics.
We can work out getting a higher powered test platform to work
We can
on.
literally just take a 54 millimeter tube and stick some fins on it.
Yep.
Like, we don't need to make it complicated, like,
I think that'd be a great idea.
no, just tube and nose cone.
Your name for avionics or payloads questions before we give it back. I guess I didn't really go over this at the start. But basically our project goals for Spectre are to launch a hybrid rocket at the Friends of Amateur Rocketry launch site to 25,000 feet. And also fly a low altitude test launch at the Purdue Dairy Farm. That test launch will include our 2 payloads, so our 418 payload and our water ballast. The FAR launch will not include those 2 payloads. And our final objective is to develop a hardware catalog that can be utilized for our future team projects. So like if we want to use our tank for another rocket down the line, or our combustion chamber or other parts, that hardware will be available from the Spectre program, and there will have to be a complete hardware redesign for manufacturing phase for certain components. So this is the vehicle overview. We are using an 8-inch fiberglass airframe, 8-inch oxidizer tank with a 6-inch combustion chamber, stem to go to 25,000 feet. We refer to the propulsion stack as the oxidizer tank and below, and the recovery stack as everything above the oxidizer tank. The recovery and payloads, as you saw, is what includes our avionics payloads and parachute recovery systems. And so for our flight simulations, we had two different methods of predicting our altitude. One of them being open rocket, and the other one being a 1 degree of freedom linear altitude simulation that's wrapped around our propulsion simulation. These are the results from the 2 simulations, the average altitude of the 2 being 24,500 feet. The stability for the rocket throughout the flight is 1.55, with a maximum Mach number of about 1.4. That velocity off the rail that you're seeing is currently sized for the far 60-foot rail. So that's where that number is coming from.
What is it on the 20-foot rail we have?
The 20-foot rail, I believe it's 80 feet. No, it's probably not 80 feet. It's probably, I think it's about 60 feet per second off the 20-foot rail. I have to.
I don't remember like the min, I think the min recommended is like 75 feet a second, I think. I'll have to look back
hang on.
I don't know. But
I'll
double check rail because when I was trying to fly off the rail too and realized hopefully this will be done before you guys fly, but the pads we got are not big enough. You have to use the launch trailer.
Right.
And just make sure that the 80-20 is attached to the trailer. I'll show you what that means, but I'm just putting it out there so you.
Right. Yeah. Yeah, we worked with the trailer a bit last semester, so I'm familiar with how the.
Yeah, so install the 80-20, so we had to buy more. So that was just kind of hanging out, so.
Yeah. Okay. Is any questions about like flight simulations before we get into propulsion stuff or the project in general? We're going to get into propulsion. So here are our propulsion system requirements. The engine shall deliver the vehicle to at least 25,000 feet. The engine shall deliver no greater than 9,200 pound-seconds of impulse in order to comply with FAA Class 2 rocket impulse limits. This is to avoid signing that 90-day in advance waiver to try and give us a little bit more flexibility on choosing our launch day. The engine shall deliver a thrust-to-weight ratio of 8-to-1 upon takeoff. And the engine and its ground support equipment shall be capable of nominal safe operation at and adhere to the safety standards of Zucro, Purdue Dairy Farm, and the FAR launch site. So here is the overview of the engine. It's an O-class blow-down hybrid rocket engine running nitrous oxide oxidizer and HTPB fuel. We are supercharging the tank to 1,000 PSI tank pressure. And we are estimated to have about 1,710 pounds of takeoff thrust with an average with a startup chamber pressure of 560 PSI. The architecture is an 8-inch outer diameter oxidizer tank, aluminum oxidizer tank with a 6-inch outer diameter aluminum combustion chamber. Any questions on requirements for system overview for propulsion? So we are expected to have a takeoff thrust of 1,700 pounds. That brings our thrust to weight ratio at takeoff at about 10-to-1, with an average thrust of 1,500 pounds and a burn time of 5.3 seconds. Our chamber pressure is a maximum of 560 PSI, with an average PSI of 500, and our tank VOP is 1,000 PSI with an average pressure of 820 PSI. So we're going to get into hardware for the propulsion system. So here is the combustion chamber assembly. Towards the forward end, which is the left end, is the inlet for the oxidizer feed system that comes from the combustion chamber. Above that is our run valve and oxidizer tank. Mounted to that closure is our injector. And then below our injector is the space for our pre-combustion chamber that has extra phenolic liners lined inside to give it extra protection as there's no fuel in that region of the combustion chamber to thermally protect it. Sitting on top of our fuel grain is our igniter. And then down underneath our fuel grain is our nozzle and nozzle carrier assembly. Both of these closures are bolted closures into our combustion chamber, and we'll get into their designs in a minute. Any question on overview of the combustion chamber? Do hide floating controls. Turn this tab back into like all tab.
So my name's Safe. I'm responsible for the injector. So this is our injector. It's called a cavitating venturi injector, essentially a shower head injector, but with cavitating venturi orifices. The requirement for this is that it must choke the flow of oxidizer at a range of operating conditions. It must also be able to achieve an oxidizer mass flow rate of 6.7 pounds per second per our propulsion requirements. I've attached some of the specs. So it's made of brass 260 cartridge brass. It contains 32 orifices and it's been rated to a minimum safety factor of 3.2. The change from our PDR is we've just reduced the number of orifices slightly to accommodate a lower mass flow rate, but that's, and we also changed to a different alloy to increase strength. This is a close-up of an injector orifice. So notice that there are two sections. There's the chamfered inlet and then there's the diffuser. The line in between is the throat. The idea behind this geometry is that it is able to drop the pressure of nitrous oxide down to 55% of the vapor pressure, which we've determined is sufficient to cause cavitation, and in doing so, minimize feed-coupled combustion instabilities. We ran some CFD to validate our model. So the color gradient at the throat is indicative of an area of negative pressure, which is in line with our expectation that the pressure at the throat will be significantly lower than the combustion chamber pressure. One of the most notable geometric parameters is the diffuser half angle. So it's currently 0.596 degrees, and that corresponds to a specific drill bit, a tapered drill bit we're going to use to drill these holes. So that's the manufacturing method for that. Questions?
How are you gonna validate the geometry when you machine this?
So we're going to run a cold flow test, and then we're going to measure the mass flow rate, and then depending on how much it deviates from what our model outputs, we're going to drill more holes to accommodate for the need for additional mass flow rate.
So you're going to assume that your CD is correct and that your machining is off. If you put mass that's different from what you think, is that correct?
Yeah, so the CD is sort of the unknown parameter here. We've used an estimate we got from literature, and then if our mass flow rate is off, then that's the cause will be that the CD is not quite what we predict or what we expected it to be.
What I was saying that if the CD, if you machined it improperly, right? You could be chasing something and it's actually the CD or whatever, right? So I was saying, how are you gonna isolate? I agree with you for the CD test. Yeah, that's sure. But you're gonna buy like pins and make sure, there's a sufficient amount of tolerance or each of the orifices, you know what I'm trying to say?
Yeah, so we do have, I have listed tolerances, so we can drill to an accuracy of 2 thou, and because the angle is so low, that translates to a variation of less than a thou with the inaccuracies due to machining. Hugo, is there what you said? Is there a method in which to measure the precision of geometry?
Pins would be one option, but since we're buying multiple drills, just in case one breaks, we don't have to wait for the other one to arrive. We can use the drill itself to measure how well the hole was made. Of course, not all drills are made alike, so there's a chance we may have to use the same drill that we used to make the entire injector, ideally the same one, to measure how much stick in or stick out we have the exact dimensions. Any inaccuracies with that method are as good as we're going to get, just because if we have to rely on the drill being so precise. There's nothing we can do to the drill is half or 1/10 of a thou off. So we're kind of sold in that aspect, but we will make sure to measure the depth that the drill reaches to in every hole, and to at least ensure that that parameter is to our satisfaction. It's a blanket statement for the rest of the slides, right? Have some sort of metrology, that's the word, right? Have some sort of validation plan for your machine, right? And it'd be the biggest difference for your part, right? You're not, airframe's not gonna notice it, the PAL, you will. Got it, cool.
Steve?
Yeah.
What sort of feed instabilities are you expecting to encounter, which causes the need for the cavitation?
So we've seen in literature pressure oscillations that cause the pressure to spike to 1.5 times nominal pressure. And although it's very difficult to predict accurately what sort of how the magnitude of those instabilities, they can cause overpressures, which could cause us to blow the chamber. They could also, the high amplitude vibrations could also be damaging potentially to payloads or avionics.
Okay. And are you referring like acoustically, like with pulsations in the flow rate?
No, maybe amplitude was not the correct word. I meant to say fluctuations. Like if the fluctuations are very severe, then that could cause damaging vibrations. That could produce damaging vibrations.
Okay, I guess hope, it is more experimental because those sort of fluctuations aren't really like. We're hoping to not include like. Such drastic fluctuations shouldn't be occurring anyway. It's like, I'm not sure if the cavitation itself is gonna stabilize those, but that makes sense.
Yeah, I mean, it'll. Theoretically, at our scale, we shouldn't be encountering any acoustic instabilities, but if there are feed system instabilities, which there may be, this should definitely reduce the magnitude of those.
Right, I mean, the injector itself is gonna be inherently like turbulent and unsteady, so I don't think it's gonna be too impactful. Upstream, but
I mean, I have looked at papers where this specific design was implemented and that has led to a significant drop in the magnitudes of those instabilities. So will likely have significant effect, assuming unless the instabilities don't exist in the first place, but I think that's unlikely.
This is maybe jumping ahead a little bit, since you mentioned the change from PDR. Were you guys able to find some papers or data to match up with your desired?
Yes, we did, and we actually lowered our mass flux rate by like 15 from the last one, so it was previously like 65. Now we're at like, oh, it's more like 20. I think our maximum is 40. It's on the spec sheet there, but the maximum is 45, an average of 32. We've seen rockets with averages of like 42 and 48. And
With
some
the size.
Yes, with the
Okay,
size.
okay.
Yeah. And there was some research that was done with the power grid hybrid rocket where they pushed their mass flux region to as high as they could. They recommend sub 60 grams per centimeter squared is when they started to see the chugging instabilities. But yeah, so we brought it down to sub 50 max because we thought that was gonna be the perfect. Cool.
This is our forward closure. So this sits at the top of our combustion chamber. It mounts to the casing through these radial counterbore holes. It seals against the sides through these O-ring grooves. It also allows the injector to mount to the bottom through these holes. And then the feed system obviously mounts to the top. It contains two ports for pressure transducers, one to measure pre-injector pressure, and then one to measure one to measure combustion chamber pressure. These are some of the geometric parameters. So it was rated to safety factor of 4.3. We're also machining it out of aluminum 6061 T6. Yeah, this has been modified since PDR. The comment was that there wasn't enough material around this port to create threads. Also, this was dropped to like here, and there wasn't enough clearance to be able to tighten PT. So we raised the hole and we added more material. And this is what the full assembly, the full forward closure assembly looks like with the various O-rings and the various fasteners. And then these are some specifications that go into the details and specifications of the various O-rings and fasteners.
Yeah, so like I mentioned, the major change that we had from PDR with regards to our field grain geometry, was that the port area, we opened up the port area to bring down our mass flux to, currently our maximum mass flux is 46 grams per centimeter squared. For reference, we've seen a lot of, excuse me, we've seen a lot of, spaceport sized rockets that have average mass fluxes, calculated average mass fluxes of within the 40s. We've seen as high as 48. Some research has been done with the power grid hybrid rocket, where they recommended less than 60 grams per centimeter squared. That range was where they started to see chugging instabilities. The port was also modified to keep the Mach number in the port below 0.3. Currently, we are much lower than that. And so the flower grain geometry that we've decided is to increase the internal surface area of the port, and thus our fuel mass flow rates for the same oxidizer mass flow rate. So we end up bringing down our OF ratio closer to our optimum mixture ratio. For reference, our optimum OF ratio is 6.8, and so you can see our OF ratio curve here. We start ox rich and then run fuel rich towards the end of the burn. Any questions with fuel grain geometry? We get into composition next slide.
Were you able to see if the mass flux rate was also for that grain geometry?
Sorry.
Were you able to find? I'm not an expert on hybrids, but the papers you read for the spaceport motors, they use a similar grain geometry.
They were cylindrical grain geometries. I haven't been able to find any papers with that do star grains. It's a little less common. So like the overlap between papers that I found with the same geometry and the mass flux range that we're in were like 0. So we were kind of basing it off of mass fluxes from cylindrical grain hybrids. So our fuel grain composition did not change from our PDR. We are using HTPB 45M sourced from RCS with 17% MDI as our curative and 3% carbon black to reduce the radiative effects in the fuel grain. The 3% carbon black is standard for that most spaceport teams use. And the curative is recommended, the curative percent is recommended by RCS. These percentages are all by mass. We are going to be casting into a 3D printed PVA mandrel. This PVA is a dissolvable 3D printable filament. So we will cast into this mandrel with plastic wrap wrapped around it. And we will dissolve away the mandrel once we are done casting. We're going to cast directly into our outermost phenolic liner. So that was another change from PR. Was originally we were going to cast into a cardboard casting tube, but it was pointed out that we probably should not pour water over our cardboard liner, which is pretty smart. So we are going to cast directly into our outermost phenolic liner. So that makes our fuel grains diameter go up a little bit. This phenolic liner is resistant to water. So any questions about like our fuel grain casting or composition?
Hello, everyone. I'm Alex. I'm one of the propulsion co-leads, and I'm responsible for designing the nozzle carrier. So the purpose of the nozzle carrier is to retain the nozzle inside of the aft part of the casing. It works similarly to the forward closure, so it's a double piston seal O-ring using those hard dash 354 Buna O-rings. We are planning on using RTV silicone sealants in between the carrier and the nozzle to prevent gas bypass around the nozzle, as well as just securing it in place. It is pinned to the outside casing, which is a 1/4 inch thick aluminum by 6 7/16 grade 8 bolts. These were calculated to be have much higher factors of safety than two, so they all look good. The bolts are counterboard, as you can see, so they'll be machined flush, so that we can slide our centering ring and everything we need to slide over onto the casing. Oh yeah, here's those factors of safeties listed out. Our lowest one is in bearing, which is similar to both the casing and I believe the ox tank. Bearings tends to be our lowest factor of safety, but they're well are rated up 2. So here's a close-up diagram of it. As you can see in the upper part, I guess I can point out here. In the upper part, which is the post-combustion chamber that's below the fuel grain, there will be a triple layer of liners. One of them, the innermost being a post-combustion chamber liner, or the phenolic liner that was sourced from the 2016 hybrid, one of the older hybrid projects. That will just be in the post-combustion chamber, so just below the fuel grain, as will the casting tube. The casting tube is sourced from Always Ready Rocketry, that came with our outermost full length liner. That will also only be in the post combustion chamber. It's mostly there, one for extra insulation, but also because it allows a better fit between our outermost layer and our innermost layer of phenolic. So that's its purpose. As you can see, highlighted in red here, that's the location of our RTV. So we will RTV the graphite nozzle, which is super iso molded graphite, that will be machined at one of our alumni's residences. And so basically the aluminum and graphite will be permanently joined. So it will slide on install and on when we take the rocket apart, those two pieces will be together. And then yeah, that's pretty much all of this line. So any questions on nozzle carrier? We'll get to nozzle in just a second.
We're not able to find the shorter bolts.
The shoulder bolts, yeah, we're not able to find the shoulder bolts.
They were that short, or it's not at all.
I think you talked to that, Simon, the shoulder bolts, shoulder bolt sourcing, because we look for them for the ox tank as well.
Yeah, shoulder bolts. I had a little bit of difficulty sourcing them. Primarily, they're just really expensive. Yeah. And because the forces from the combustion chamber in this case are relatively low relative to the size of the bolts, we weren't super concerned about them.
Yep. I'm sure when you guys do an abbreviated version of this with Scott later on, I would have the math for the O-ring sizing.
Okay.
So you show your work.
Yep. Sounds good. The nozzle itself, like I said, will be made out of ISO 2020 graphites. The throat diameter is 1.6 inches and the exit diameter is 3.89 inches, which gives it an expansion ratio of approximately 5.9. It is sized for sea level or ground level exits pressure, and the angles are listed there. Like I said as well, machined alumni's residence on a lathe. So, any questions on the nozzle itself?
All right, hello everybody. My name is Simon. I'm the other propulsion co-lead, and I'm also the responsible engineer for the flight tank. So kind of some top level specifications. We're looking at a volume of just over 2,000 cubic inches. We have a maximum allowable working pressure of 1,200 PSI. We plan to hydrostatic test it to 1,800 PSI. It's designed with a safety factor of 2, which brings us in line with Spaceport America Cup design guidelines. It'll be primarily constructed out of 6061 T6 aluminum. It's an outer diameter of 8 inches with a wall thickness along the primary length of 1/4 inch. It's just a hair over 53 inches long and weighs a bit over 42 pounds. For ports, we plan to have a 1-inch SAE ORB port on each head as our primary port. On the aft head, we will have a 2 1/4-inch SAE ORB ports to give us a little bit more access for instrumentation. Both of the heads are built with integrated Radax coupler joints, which we'll discuss a little bit later. And then the heads are bolted to the tube itself with bolts. It's a bolted closure with O-ring seals. And we chose that over a welded design because it gives us a little bit better in-house manufacturability. And there were some concerns about the welding process damaging the temper of the aluminum. So looking more specifically at the head design here, like I mentioned, it's a bolted design with O-ring seals. Those O-rings are -365 90 durometer nitrile O-rings. We'll run those with contoured backup rings just for a little bit of extra support at these elevated pressures. The bolts will be 2 rows of 10 3/8 by 20 radial button head bolts. And those will be secured with nuts. There are flat faces machined on the inside of the head to support those nuts. The geometry is torus spherical. It's fairly close to 2-to-1 ellipsoidal, deviates from it a little bit. That was selected to minimize both weight and length to sort of limit the size of stock that was required to manufacture this. And the heads have a safety factor of 2.13 from FEA analysis. Any questions about this?
Yeah, why'd you go nuts over just tapping the wall?
There were some concerns raised at PDR about the whether there was enough thread engagement with just tapping the wall and adding nuts we found to be a little bit lighter than thickening the wall to increase our thread engagement.
Technically, yes, right, like, I follow the logic. Practically, that seems kind of odd. You know what I'm saying? Like, I agree with what you said, you're correct, but I think practically getting all those nuts in there is gonna be a fun time.
Yes, I recognize that this is going to be a tedious assembly process.
Okay.
Yeah.
Are they at least gonna be well nuts, or not well nuts, sorry, block nuts?
Yes, we use block nuts with the little on them.
I don't really remember this in PDR. They thought that there was not enough thread engagement, but it's just a pin. Isn't it? So
yeah, the tensile forces aren't the primary thing acting on the bolt here.
Right.
But once you get really short with your thread engagement, questions start to be raised about the movement.
I've had a hard time finding a good source describing the required thread engagement for bolts used in this manner. I've looked through Shigley's and a few other machine design textbooks and haven't found any information. I met with a professor who didn't really have any super strong input either. So just sort of, if I can find a good resource that would suggest that is a acceptable design choice, that's would be preferable to be a little bit of a simpler design, but I don't want to pursue that without the literature to support that decision.
So, I mean, if you just assume they were the minor diameter only, right?
Yes, which is what like these calculations here are all.
So what's the problem with the threads then?
I think the concern is that
because you could just pin it, right? I mean, I know you're not because you bring a permanent, right? But you could just pin the thing, right? You still have the same engagement there. So I guess I don't understand why.
I guess it's a little bit like that was my original thought process as well. And that's why I presented the design at PDR. But we got a little bit of pushback from Scott about that design choice.
Pushback from the thread engagement,
like thread engagement. He was recommending for thread engagement.
That's where we had the shoulder bolt discussion.
Was up here?
Yeah, this was where the original shoulder bolt discussion came up.
Right, and then you also just explained a second ago, because these things are so thick given the size, it doesn't matter.
Yeah, well,
I think you're right.
Yeah, I'm a little bit more comfortable with the
I think-
oxide or with the
Yeah.
combustion chamber where the loads are that much lower.
Yeah.
The axial load on these heads is tremendous. I think it's in the realm of 100,000 pound force. For all of it. Yeah, across the entire surface area. Yeah, it's certainly something we could look into. There are some alternative like non-permanent pins we could also explore.
Spring pins.
Yeah, spring pins, or they make, the button detents. We could continue to explore those a little bit more, and see what some alternatives are.
Yeah, because I just think you're gonna hate your life doing those knots.
Yeah,
and it's like I said,
it's not a pretty
technically,
solution.
like, in theory, you have the right answer, but I think practically it is gonna be a pain in the ass.
Yeah.
Ideally, this would get put together and never get disassembled.
Ideally.
Yeah.
Yeah.
Yeah, we'll continue to pursue some design alternatives.
Like I
for this
said,
and-
make a drawing of this too, right before we machine it, and we'll have a little bit of a look. I think. I think Scott probably underestimated the thickness you have on there. Even that's what,
It's 1/4 inch.
to go through?
The distance from here to
Oh,
there
okay.
is 1/4 inch.
Yeah, the nut's a 1/4 inch. Is it not?
But you have
Yes.
additional.
I know, but like, if you talk about too much thread engagement, okay.
Yeah, I think then. They generally recommend more thread engagement between steel fasteners and aluminum tapped threads than between steel fasteners and. But yeah, we'll.
We're gonna save you work, that's.
Yeah, and I appreciate that.
Okay.
Yeah, I've been on a mad hunt trying to find some good design guidelines
Yeah.
for, it's a very non-standard bolt application.
Yeah, I think generally it's recommended just 1 to 2 times diameter. Just so.
Yeah,
That's for, tension, right? You're not, it's
Yeah.
not, but true.
all right, well, we'll move on and circle back with that at a later date. So yeah, there are some of that structural analysis. Bolts are gonna meet our safety factors. We've designed the tear out to be the lowest factor of safety. Just to helpfully ensure that if the tank were to fail in an overpressure scenario, it would fail through the heads as opposed to out, and hopefully limit the potential damage that would be caused in such a scenario. And then you can see the calculated wall stresses there as well. Are there any other questions about the flight tank? Chris or anyone on the Zoom? Okay, move on. So I'll be presenting the forward tank instrumentation manifold next. So this is a manifold that'll be located on the forward end of the tank towards the top of the vehicle, with some instrumentation and safety relief devices. Safety factor is greater than 5 from burst loads at our maximum allowable working pressure of 1200 PSI. The failure mode that we identified would be thread tear out through the fittings. The primary geometry, it has a hexagonal shape, and then fitting ports spaced 120 degrees apart along those faces of that hexagon. At the top, there is a 1/4 inch NPT hole through the top, which we could use for a thermocouple. And then along the 3 sides are 1/4 inch SAE ORB holes. And those will hold a pressure transducer, burst disc, and then our vent relief solenoid. And then along the bottom, there is a 1/2 inch SAE ORB port. You can see on the diagram there, the fittings highlighted in red are all adjustable. So that'll ensure that we can get everything locked appropriately to the vehicle. Is there any questions about the manifold itself? All right, move on to some of that instrumentation, or some of the relief devices rather. We're planning to have a burst disc. That'll be a high P component with a 1650 burst pressure, stainless steel. And then that burst pressure again will be between our maximum design pressure and our hydrostatic pressure. So should fail before the tank will. And then our vent valve will be a Peter Paul series H21 valve, normally open. So if there's any sort of anomaly with the ground systems or our electrical, the tank will fail safe. And then it meets all of the requirements we have of the tank. there any, or of the system rather, are there any questions about this? Okay, move on. And then lastly, the vent valve electronics. There's a small custom design circuit that will keep the vent valve closed after the vehicle has disconnected from the GSE during the initial phase of the burn. Just to make sure that the vent valve doesn't open while the burn is ongoing and cost us any performance through reducing the pressure in the tank. It allows full GSE control before the launch with no delay. They'll have full control of the GSE. There won't be like a pre-programmed 10-second delay from the GSE on that. During the flight, it'll run off 3 14500 lithium ion batteries. Those will weigh about a quarter pound. Circuit runs off a 555 timer. So it gives us an adjustable delay between about 0 and 30 seconds, which will adjust to the length of the burn. The design has been validated using LT spice simulations. And then one concern that was brought up at PDR was whether the electrical connections might potentially shake loose under the high vibrational environment of the rocket flight. So this has been swapped to JST XA connectors, which have a positive reinforcement spring clip on them to hopefully retain all of those wires. Any questions about this system?
Just a quick one. Have the batteries been sized to last the required length of time on the launch pad?
So the batteries are only turn on, or are only power is only drawn from the batteries during the time that the vent valve is kept open. So that 5 to 10 second window, whatever we size it for, the rest of the time power is provided by the GSC.
Okay.
And then the circuit handles the switch between the two. The primary restriction in sizing was the current capacity. The solenoid draws quite a bit of power. Cool. Move on to our next component, the inner tank plumbing. Once you got this. Yep.
Yep, so this is the area of our inner tank. It has changed a little bit, mostly just with the fittings. We've added some analysis to our run valve. The calculated flow velocity at our 6.7 pounds mass per second flow rate is 35 feet per second, which we deemed acceptable. The minimum diameter that this flow velocity would occur at is 0.844 inches, which is the inner diameter of our smallest fitting. And it is all aluminum fittings that are listed from our source, from our manufacturer at max operating pressure of 1000 psi. But that there's a safety factor obviously built into that. They'll be anodized black, which is important because so they don't get mixed in with these stainless steel fittings that are at Zucro. So they'll be used as 1000 psi fitting in a 6000 psi application. So first is going to be run valve.
Theo.
Vanessa.
So the run valve, our servo hasn't changed from PDR. We're still going with the same servo. We just ordered it, and when that comes in, we'll start doing some testing on it. We'll go a little more detail on that later. For the valve, we did end up changing fairly recently because we started looking into how it's going to actually connect to the rest of the piping in the rocket. And we decided to change from a standard port valve to a full port valve. So we have one, I believe, picked out. We just need to double check it and then order that so we can test that as well. But other than that, everything else is the same as PDR. This is our CAD from PDR. Our design is pretty much the same. We haven't done any testing yet, so there's no data.
And so this is our testing campaign. The main 3 things that we're going to be testing is a servo torque, actuation time, and then overvolting the servo. And so then based on that, we'll either confirm whether or not we need to change the actual servo if it meets our requirements. And so we set up the microcontroller and circuit to test that, which we'll cover on the next slide. But basically our main thing is testing these 3 things and seeing if we can overvolt the servo. Because right now the max voltage is 8.8 volts and we're seeing if we can make it more to increase it.
This is our draft for the circuit design. We're gonna use Arduino for testing instead of Seed Studio Shell, which we're gonna use it for the actual design. But this is and we're gonna use a relay to bring the voltage from the power supply, and then send that to the Arduino, and then send PWM to the servo, and then calculate how much torque it could generate and how fast it is.
Is how are you measuring the activation speed?
So we were talking about this, and like, I think our plan is to like record the servo and servo of the iPhone and just see the time.
For some of our like the actuator ball valves out of the lab. On top of the actuator, there's like a little flag that shows, hey, on and off, right? When that moves, what we did was a while ago. We actually put a contact switch on the flag and a contact switch here. And so it hits, the flag open, because the flag is directly in line with the ball. So you could do a video. I think it'll be probably mixed results. But if you actually wanted like a exact time, you could put some sort of contact on like the stem of the valve, have it swing and hit something when it's fully open to like break that contact, and you can record that time there. Does that make sense? Yeah. It's a super simple circuit too. It's not like we actually have little custom pre-propulsion PCBs for both of those ends. So if you want to take one and try to modify one for this application, you can.
Thank you very much.
You get it small enough to keep it on the vehicle, you can get the actual data.
Yeah, that would be great.
Yeah.
Stay here, that'd be nice.
Awesome. More questions?
So this is the quick disconnect, which will be attached to the rockets during the filling and allow further proceedings to occur. It basically works by it uses two Talon's 6mm stroke pneumatic cylinders to withdraw and put the two quick disconnect fittings together. And then upon actuation of those pneumatic cylinders, the fittings are pulled apart in the way that will withdraw, and then the QD will fall away. Things have changed since PDR. We've verified that the check valves are on the fitting that we're using are double-sided. So it is in fact a double-sided check valve on both female and male ends of the plug-in socket. And we also added you can see here, these spaces for the catch mechanism, which basically will be some type of paracord or some type of rope that will be attached to the launch rail, and or the I-beam for fire testing, that will just make sure it swings down. We'll make sure to test that before actual launch so we don't break anything. But yeah, like I said, the design is proven to smaller scale. The Stroma, which was our last project, used a very similar design, so we believe that this will be quite reliable. As opposed to the quick disconnect, which has been proven at a smaller scale on a rocket, the feed system interface was not proven. So, like we said in our PDR, we did a test article that has proven that it works. But basically, the purpose of it is to connect the feed system, which includes the whole inner tank coming down to the ox tank, into the top of the combustion chamber, which you can see there. It basically works by using a tube that can slide in and out from the top of the combustion chamber because of 3 O-ring seals. The requirements are listed here. It's necessary in order to unconstrain the intertank length from the length of the lower airframe. Little more information here. We decided to use 3 X-profile O-rings, which are better for dynamic seals. The reason we use them here and not for our rod seals for our tank and combustion chamber are because they're just a little bit better with dynamic seals because of the fact that they can hold lubricant in their groove right there. So during assembly, we know that it'll be lubricated joint. And as well as the fact they're less likely to see spiral failure. We also included backup rings, which are the white, sort of rectangular, cross-sectional rings you see there. And like we hydrostatic tested this test article, which is made of aluminum, in the Zucro fab shop to 1500 PSI. So we believe it'll be just as good with the stainless steel tubing. We settled on a 1-inch OD 049 stainless steel tube for our control interface. So
Lubricant are you putting in the O-ring?
sorry.
What kind of lubricant are you putting it in there?
We'll use Crydox.
Oh yeah, Crytox, yeah, that's what it's called. Okay, Crytox. Any other questions from online?
I just have one question. What are you guys doing to prevent that you, like during assembly, you don't accidentally push it too far while you're assembling? Or is that the airframe going to be blocking that?
So yeah, the airframe will be attached to the combustion chamber before assembly.
Okay.
So, yeah, so when you slide it on, it'll hit the end of the coupler basically. So it won't be able to.
Okay.
So yeah, it'll be sized, yeah, so it can. Yeah.
There's like space. Okay. And then you guys didn't have any trouble with like when you guys did your test that the O-rings didn't slip out of the grooves, right? Or you guys didn't have any trouble with that?
We had no trouble with the O-rings slipping out of the grooves, but we actually did have some challenge with upon reinstalling the O-rings with some shearing. So the first time we installed the O-rings, it went flawlessly, but we did shear a few O-rings on successive attempts. So
just buy extra.
Yeah, buy extra, as well as we're gonna chamfer / fillet the end of the tube. Probably just file it down or use the deburring tool on it. Make sure it's that inner edge is smooth so it doesn't shear those rings.
Yeah, that's a good idea.
For assembly for this, would it be possibly best if you insert the length of tube into the end cap before putting on the injector and verify, you didn't shear any of the 3 O-rings in there, and then once you install everything, you then slide that pipe up into place and connect it to the run valve instead of trying to keep it mounted to the run valve and then slide it down into the rocket motor?
Yeah, that's a very good suggestion. I don't see any issues with that, so definitely avoids a possible problem. So
yeah, just because it would suck if you're trying to assemble it and there's also no way to verify you sheared off an O-ring on insertion. If you've already got the injector cap on or the injector on the injector plate. So then you could have bits of an O-ring and flopping around inside of there or clogging up part of the injector.
Yeah, that makes sense to me. Any other comments?
Sorry, is there a reason you have 3 O-rings versus just 2 O-rings?
The reason was just because this was a dynamic seal that was kind of an unproven design. And just because of those sort of unknowns and extra requirements, we just went on the safe side.
It's probably not bad to have 3, but I'm doubtful that an extra one, like a third one versus just 2, is going to provide you much protection, because I think if they're leaking, they're probably it's probably enough of kind of an issue with all of them. But the only thing I'd be worried about with an extra O-ring is just one more to shear, which I don't think is that big of an issue, so it probably doesn't matter, but I don't think you're protecting yourself that much more with an extra 2.
Yeah, okay, yeah. Then one thing we could also just test it with the demonstrator. We could just install 2, see if that works. Similarly to how it did before. So that we could look into that for sure. That would also save us a little bit of length on that, a little bit of weight, even if it's minimal. Appreciate the comments.
Yeah, on that note, how are you guys planning on testing this? Like, I know you guys did the test piece, but for hydrostatic, how are you guys planning on making this go past? Because you're never gonna have, I assume, this assembly fully up with the run valve while you're doing hydrostatic.
Yeah, so yeah, like as you're saying, like if you install the if you install the feed system interface with just the run valve and not the ox tank on top of it, obviously it's not gonna stay in, it'll just pop that out. So we would have to hydrostatic test this either with using a plug instead of the upper instead of the forward closure, or alternatively, you could just test the have the entire system together, the airframe and the ox tank, but have the run valve closed, so you don't have to, you know, hydrostatic everything together, and hydrostatic it that way. So that's what we can do. Any other comments, concerns on its interface? All right, moving on. Electrical disconnects. This is stayed relatively much the same as before as in PDR. One slight edit to that is that because our run valve team now has moved the power for the run valve on board, we don't have to worry as much about this with the timing of the air out of the disconnect. That's just because once we send the signal, the run valve will open no matter what. So that's one comfort, that we won't have a partially open ball valve. But other than that, it stays basically the same. It handles communication for the, like I said, the aft instrumentation and controls, which is the run valve, and the TCs that we'll have down there, as well as the PTs we'll have down there, and then the upper instrumentation manifold on the top of the oxidizer tank. Any questions on this system? All right, we move on. The PNID.
Okay, so this is the plumbing and instrumentation diagram for our ground support equipment. So how we're going to load nitrous and helium into our flight tank. Our GSE is going to be using nitrogen as its pneumatic pressurant. One bottle of nitrogen is going to be supplying pressure to our pneumatic valves. So our pneumatic helium fill valve, which you can see here, our pneumatic nitrous fill valve, and our pneumatic dump valve. Will also be providing pressure to the QD actuators. This is going to be all, those four components are going to be on the same nitrogen source. And then our pump is going to be on its own nitrogen source. And the reason for this is that if we are running the pump for an extended period of time, we don't accidentally sap all of the nitrogen out of that bottle, and we're left with no pneumatic pressure left. So our nitrous bottles are going to fill into the flight tank through this blue tube here you see. So we have a pressure transducer on these tanks to ensure that they're below the vaporization pressure of nitrous. With a filter on the line, we have a pressure gauge, a relief valve that's sized to 1250 psi. We have that before and after our nitrous fill valves. And so this nitrous line goes in and integrates with the helium line in this section, where it goes through the quick disconnect and then fills from the bottom of our flight tank right above our run valve. The helium line is a similar setup, except we have a pressure regulator. The regulator is going to regulate whatever the bottle pressure is down to 1000 psi. We have pressure gauges before and after that regulator to confirm those pressures. This relief valve will also be sized to 1200 psi. And then here's our helium fill valve with an orifice to reduce the adiabatic compression of the helium once we open that fill valve. All three of these lines are going to, all four of these supply bottles are going to be run through filters and have manual vents on them in case of an emergency where a manual vent is required. I believe I covered everything. Is there any questions about the ground systems or anything on this PNID?
Why do you for PGHE 302-G, why is there a relief valve? See the filter relief valve and the regulator. I guess why do you have a relief valve? Or is that relief valve for that whole little system there?
This relief valve is for the area downstream of the regulator.
Right, I remember the one to the left of it. 302. Right there, yeah.
This is a pressure gauge here.
Sorry, okay, we're good.
Just quick question. I think you went over this during the PDR, but why do you have two TCs? One at the bottom, one at the top. Is it really necessary to get both?
So it's probably not necessary to get the temperature of vapor nitrous, although it would really be nice for doing the data reduction afterwards. The liquid is what is really required, which is that bottom TC. The liquid so that we can determine what the density of nitrous is on startup. The vapor, it's not so much as required. It might help us better characterize what the state of the nitrous was in the tank. But that TC is not required on the top.
So it's like because you're getting the data.
Right, exactly. Okay, if there's no more questions on the PNID, we're gonna move on.
Hello, my name's Thomas.
I'm Paris.
We've been working on the K1 stand, and there's been a pretty big shift since PDR. We decided to move from the inverted stand to just like a regular upright bottle stand. Some reasons for this is because it was a little difficult to find a way to add a load cell mount or a load cell to the stand, and also the loading process was a little complex. So now we're just using a dip tube with the upright bottles, and we've used like basically the same design, but we've just added the load cells onto them. And
Consider the load cells we're using S-type load cells, 440 pounds, also 20 kilograms. We're thinking about having one, trying to put one in the center, but it wasn't really gonna work because we were kind of worried about like messing with the plating and stuff. So we decided to just have two. We might, if we find one that's lower pound force and would still be feasible, we will switch to that one, but just for the sake of making sure we have enough support. Is we place in between two plates, and it'll compress, which will be able to tell how much weight is.
First of all, I appreciate you guys realizing, hey, just redo the whole thing. I noticed that and I appreciate that. Why? I remember there's a comment being about the chain instead of a strap last time. I guess why'd you guys go with the chain?
The chains in the CAD just came with the bottle.
Okay, I get you. Okay, yeah. Okay, cool. That's it. Okay.
They'll be both chain and strap, most likely.
Okay, very cool.
And just for reference, the height, like the height that we're having to lift the bottles a lot less comparatively. So for like tipping calculation we did a lot earlier, it's actually a lot better now because it's closer to the ground. So it's less the angle it needs to tip would be higher.
Cool.
So basically just a safer, easier to set up model.
The other questions?
So is the reasoning for this because you can't get a low range load cell with higher resolution for the test stand for static firing, since you'll need to also have it take the full force of the rocket?
Yeah.
Okay. But for launch, have you considered just putting a load cell on the rocket itself? That way you're not getting the mass reading of all the stuff you'll be losing in the lines leading up to the tank?
Yeah, we are considering putting a load cell on the rail. We'd have to work out what that could be, but what we plan to do for what you mentioned with the volume that you're losing inside the GSE, we plan to measure the volume of the nitrous line once it's all set up. So we can estimate, based on the temperature of the nitrous, we can estimate how much nitrous we're losing to the ground support equipment at a given time.
Any other questions?
Sorry, did you say you're measuring or like you're gonna calculate it?
We're gonna measure it. We're gonna use water and we're gonna measure.
Oh, measure the actual, okay, okay.
Yeah, so you're using water when you are doing your hydro test, right? So you're just going to measure the lines empty and then measure them full, take the weight difference to get a rough volume calculation is what you're saying?
I'm not sure what you mean by hydrostatic test, but we'll fill the, we'll just use like the DI line that's in the Zucro fab shop, and we'll fill the nitrous line.
Okay.
With water.
Yeah,
And
because
measure that on water.
okay, sounds good. Yeah, because I thought what you guys were talking about earlier this semester was when you do the hydro test for the tank, you're just going to, while you're doing the hydro test for the tank with the DI water they have to fill it with anyways, you might as well weigh it dry, then weigh it completely full, and make sure you got all the air bubbles out of there. That way you can get a rough estimation of everything, the entire tank volume from the run valve up to the vent valve.
Yeah, we could do something similar to that as well. But I think the current plan is to do the measure the volume of the water that we get inside of the GSE.
Mm-hmm.
Hey guys, my name's Nick. I'm the data and control specialist for the prop team, and I'm in charge of the DAX. So nothing's much changed from PDR. It is still inside this box. We have started reintegrating the 6343 into it. We can get it to do control. We're currently on a testing campaign right now to, it's kind of just a software to hardware integration campaign, trying to get the Zucro Lab view to connect with the 6343. So that way we can use it for when we decide that we want to test our rocket and also launch. Wiring diagram, the exact same. We only have digital outputs from our relays and we get analog inputs from our PTs, our TCs, and our load cells. And yeah, is there any questions about what's going on here?
Just call back to the valve actuation team. If you wanted to get fancy, you could put that switch on this board. So when you guys test, not only do you have a 0 time when your thing starts, but you can see when that valve was full open. So if anything weird happens in your startup, you have some sort of just another data point.
Right.
Nick, did you figure out the PWM? Are you guys just using the nano pretty much, and that's how?
We're using the nano pretty much.
Okay, that sounds like a good idea. Okay. Also, just one thing. I know you guys are pulling wires, or you guys aren't pulling wires anymore before the servo, right? Because it's all on board. Okay, never mind. Never mind.
Thank you, Darshall.
Right, I'll be presenting the test stand that we plan to use for hot fire testing. It's primarily based on the proven Zucro flexural test apparatus that's seen a lot of use by the PSP teams and by hybrids in the past. We built a aluminum 6061 bracket that will interface with the rocket itself and transfer that load into the flexural apparatus. Plan to use an interface 3,000-pound load cell to record our thrust, and then as we've discussed previously, we'll be measuring the K-bottle mass to find our recorded nitrous oxide mass for the burn. See a few more detailed pictures there. The overall dimensions, it's a 1 foot by 1 foot aluminum plate, and then it'll mount to, we have a hot fire airframe coupler with 4 half-inch bolts, and then the test stand itself is constructed of a few different pieces of aluminum that are all bolted together with more 1/2-inch bolts. And then it uses the 3/8 bolt holes that are already on the flexural test stand. Go over the airframe coupler. So there you can see the rocket mounted in the stand. And then the airframe coupler that we're planning to use for this. So construct a separate section of aft airframe that will be used only for hot fire, not for launch. And included in that will have an aluminum coupler that'll meet between 2 separate fiberglass sections, using a similar system to the airframe couplers that are at the top and bottom of the oxidizer tank. And then it'll have give us a nice spot to grab onto the rocket with the test stand. And then we'll adjust the lengths of the 2 pieces of airframe to get the ideal positioning of the rocket above the flame diverter. Are there any questions about this?
Right, the whole thing's gonna be reacting against that fiberglass too.
Yes, along the bottoms.
The boat tail reacts to thrust, so that's all we'll push up.
I'm okay with that, Scott, I don't know. My Scott tense is tinkling on that, right? I think it's probably fine, but he may have something to say about that, but I wouldn't worry too much about it. Cause in flight, it's gonna happen. Right? So.
Right.
Moving on to our couplers, you will describe those.
Hi, my name is Hugo. I'm the team's manufacturing specialist and also the engineer responsible for designing the system that will join the oxidizer tank to the airframe, both above and below the oxidizer tank. So this comes in the shape of 2 upper 30-degree redox couplers with aluminum 6065, 61, 6. They will be joined to the tank and to both ends of the tank caps into female versions of this geometry that's already been designed into them. And then the airframe will attach to the thinner surface. The idea behind this is that we over machine them by approximately 5 thousandths of an inch, cool them down to about 0 degrees Celsius, so freezing, and turn them into the airframe, allow them to expand. We predict about 5,000 pounds of force from that expansion, but we're not too sure on these calculations. So on top of that, we're riveting the coupler into the airframe after the assembly is complete and after it sits rigid. We confirm everything is vertical. We will drill 2 rows of 5 holes through both the airframe and the aluminum, that we will then proceed to rivet with 3/16 1/4-inch long steel rivets, and then we will just flare. This joint will be semi-permanent. We can take it off if we need to, but the driving idea behind this is that if we need to remove something, we'll remove the copper from the oxidizer tank. That's just joined in by these holes down here, the 6 1/4-inch 23-inch long bolts, grade 8. There is an assembly on the next slide where you can see what this will look like. The rivets aren't completely flared because that's just how the CAD program comes. But we already have the tool for this. Now we can see some of the factors of safety for the bolts and the rivets. The pins here were the previous design that we presented at PDR, but after some feedback from Chris, we just decided to study the idea for a riveted joint that seems it looks better mostly, but it also has been proven effective in the past. And it doesn't really add any complexity to it. We already have the tool to do most of the work, so we don't predict any difficulties in assembly. Does anybody have any questions?
How do you plan on holding that coupler when you machine it?
So the thinnermost section, that's 1/8 inch, we will machine the entire outer surface and the specific geometry that's important in a lathe. whilst leaving a very thin material in the, where it's supposed to be thin. Once that is done, we will put this into a mill and using very light operations, remove all of the excess material in this section until we're left with our approximately 1/8 thick section that will be joined with the airframe. Since the internal surfaces aren't of particular importance, we can afford to do this in a mill that won't create a perfect circle, but the outside surfaces and the specific geometry that mates to the oxide does need to be precise, so that is done on a lathe. It's 2 operations, and fortunately, we will be able to buy the stock for this as a tube. Turns out buying tube is more expensive than buying the actual aluminum round as a solid, except for thicknesses below 0.5 inches. So the difference between the innermost radius and the outermost radius or diameter in these is 1/2 inch, set lower than 1/2 inch. So we can afford to buy tube that is still slightly cheaper than old stock, which makes my job a little easier. Also, something I forgot to mention, they are designed to work for 5,000 pounds. Jasper mentioned that's not going to be our actual parachute deployment force. This is mostly because we began design for these a while ago, and we weren't sure what that was going to look like. So just decided to go with an extremely high number that ideally, even if our system architecture changes to the point where we need more parachute deployment forces, we don't have to make these. This number mostly depends on the number of bolts. The aluminum itself is fine. And so having 6 versus 4 bolts is just a very non-complicated design choice. Any other questions?
If you're already riveting it, why do you need it to be the interference that needs to be heated? Because if it ends like I'm worried that it will end up not being able to fit in or be really difficult to fit in. And once you've machined out the inner side, there's really nothing to hold on to. So you can't, unless you're going to manually sand down the outside of the coupler, there's kind of no way back. And if you have the rivets, it seems like you could have a little bit bigger tolerance and not really lose that much.
Yes, for this design, this was actually a suggestion by Chris, and I like this idea. One of the bigger issues with coupler designs was that to make sure that the entire rocket still sits vertical to itself instead of slightly tilted to one side, which is what sometimes tends to happen. By having our coupler physically press against the airframe, we ensure that there is absolutely no slack at no condition, regardless of temperature outside. And because the rivets don't provide a perfect joint, there is no guarantee that the rivet will make sure there's absolutely no movement between the aluminum and the airframe. This design seems better, and I am fairly confident in my ability. This may sound a bit strange, but I don't foresee any problems in actually fitting the airframe, the coupler into the airframe. Even if I somehow manage to over machine or have an excessive diameter, we can just cool the coupler down further. It's only targeted to 0 degrees Celsius. It's not that cold. Freezers go to much lower than that, so we'll just reduce it by another inch, thousandths of an inch or so. I don't expect, even the lathes on their own without no supervisions would give you tolerances that are about 0.02 of an inch. With specific intent, you can get them lower. So I don't foresee trouble in these parts. Fortunately, they're not particularly expensive parts to make. They're just time intensive. If the mistake is made, and that'll be my bad, so I'll be just perfectly happy to remake one of them. I don't know if that answers the question.
When we machined a lot of our parts, we had much smaller parts, but we had difficulty getting it down to that tolerance. Like experienced machinists, I'm sure, have a lot easier time getting it into good tolerance, but I would definitely be worried about remaking it. And then if anything is off, that wall is pretty thin. So I'm kind of worried about that. And then you're also drilling holes into an angle at that coupler. How do you intend to do that? Because it seems like you'd have to um hold the part from like the thin end of the flange to be able to get those angled holes in.
The holes themselves, these holes will actually be drilled before the rest of the part is done. Bagel has a 5-axis CNC mill. Even if we don't use a 5-axis, we have other options, but that would be ideal. The protocol for most holes, at least in Bechtel, is you drill a hole first, and then you machine the rest of the geometry around it. Holes tend to be the most sensitive pieces to some of these to machining. So the idea is that once we get the tube and we verify that everything is good to manufacture, we will begin by drilling the holes and then put the entire thing on the lathe. I don't foresee problems with this, but to be honest, I've never made holes at an angle. Other people in Bechtel have. I'm not particularly worried about it.
Yeah, I feel like it's more complicated to do holes at an angle, but it should be doable. I'm mostly worried about the interference fits and the just thinness of the wall. I'm not super experienced with manufacturing though, so but sounds like you're thinking about all the right things.
Okay, thanks. To make sure I get my point through, by the time when we make these holes, this feature won't exist. This entire tube will be 1/2 inch thick. So there won't be any complications in actually work holding it. When we're making the holes. And this will actually remain 1/2 inch thick for most of the manufacturing process. It's only at the very end, that we actually remove all of the extra material in the inside and reduce it to 1/8 of an inch. That's why that's the last step. If anything goes wrong before that, we still have a good surface to grab onto.
Just one quick question. If I'm understanding this correctly, you're screwing in the radix joint from the outside or the inside of that airframe?
The bolts come from the outside. This
Okay.
section doesn't show it well. I thought the pins would be more important. They're not aligned, unfortunately. These are socketed bolts. They stick into out of the airframe a bit, but the holes that need to go through the coupler, the oxide head, already disturb the airflow to the point where having bolts sticking out not much won't present any further problems. There's also lower profile head bolts that we can look into using. It's just lower profile head also means less clamping surface for your tool, and we're gonna have a bigger risk of stripping the hex.
Sounds good.
The event, we do go take out the ID, you're clamping from the OD, correct?
In manufacturing.
Right, so when you do the ID, you're gonna clamp out from the outside, right?
So I'm always clamping from the inside in this process.
Even when you do the ID.
When I do the ID, we will still be clamping from the inside. I'm not going to clamp from the outside on a critical surface. But since there's not that much actual surface you can clamp to, it doesn't really matter. There's only a thin section here you can clamp to. The process will be just taking very thin and very low depth of cut.
I guess my point was getting to was, if that becomes a problem, you could just make it the other half.
Yeah, and hold it to the yeah. We got some soft jaws that don't leave indentation marks.
Right, I just make sure you're thinking about you can make the other side. Cool.
This manufacturing process is not extreme by any means. It's just has to be thought through. That's good. I believe we're done then, right? That's our friend.